Hello students, welcome to my channel. In the old times, in ancient world, suddenly people noticed that there were small pieces of mineral magnetite. These mineral magnetite pieces were magnetized pieces, and these were able to attract small pieces of iron. These small mineral magnetite pieces were called the lodestones. It was then that the concept of magnetism was introduced. For the very first time, an Indian surgeon named Shastra used the magnets for the surgical purposes. So, now we will discuss about the definition of magnets and magnetism in physics. What are magnets? Magnets are the objects which have the ability to produce a force in order to attract other ferromagnetic materials such as iron, steel, etc. So when they produce a force, there are certain invisible magnetic field lines that are also produced due to the influence of which certain ferromagnetic materials get attracted to the objects which are called the magnets. Now, what is magnetism? Magnetism is a phenomena by virtue of which there develops an attractive or the repulsive force. So this phenomena of developing the attractive or repulsive force is called the magnetism. Now there are different shapes of magnets. The most common shapes of magnets are visible to you in the coming slide. They are the horseshoe magnet, the bar magnets, disc magnets, spherical magnets, ring magnets, cylindrical magnets, etc. Just look at the picture here. You can see a U-shaped magnet, a cylindrical magnet, a bar magnet, a horseshoe magnet, a button magnet or a disc magnet, a ring magnet. The magnets have two poles, the north pole and the south pole. All the magnets have two poles at the two ends. They are the north pole and the south pole. So we can say that the magnets are bipolar. Now let us look at the picture of the disc magnet. The north pole is on the upper side and the south pole is on the bottom side. If we divide the magnet into two halves, the red and the blue one, the above point is called the north pole and the lower point is called the south pole. Here also you can see the ring magnet is in an imaginary way divided into two different colors, that is the red and the blue color. If we imagine the circle magnet to be axially magnetized, then the north pole is on the upper side and the south pole is on the lower side. But here it is diametrically magnetized. So you can see the north pole is the left side, the south pole is the right side on the upper half, and on the lower half of the magnet, the right side is north pole and the left side is the south pole. So it depends upon if the circle magnet is axially or diametrically magnetized. Now let us come to the properties of the magnet. Magnet attracts ferromagnetic materials like iron, cobalt and nickel. Like magnetic poles repel each other and unlike magnetic poles attract each other. And the third one is a freely suspended magnet always points in the north-south direction. You can see the diagrams ahead. which will help you in understanding the things better. If we take two bar magnets, we will see the south pole of the magnet gets attracted to the north pole, and if we place two south poles of the two magnets near to each other, they will repel each other. Whereas if the south pole of one bar magnet is kept near the north pole of another bar magnet, the two magnets will attract each other. If we talk of a freely suspended bar magnet, as shown in the figure, the bar magnet will point out in the north-south direction. The direction can be confirmed with the help of a compass, because when a compass is freely kept, the compass will point out in the north-south direction. Similarly, when a freely suspended magnet is kept and hung with the help of a stand and a silk thread, the bar magnet will point out in the north-south direction. Now there are different types of magnetic materials. They are the diamagnetics, the paramagnetic, the ferromagnetic, the ferrimagnetic materials. Now what are diamagnetic materials, or what is diamagnetism? Those materials which are less susceptible to magnetic fields are known as diamagnetic materials, and they exhibit a property called diamagnetism. Means these materials are not much affected, they are not much magnetized, because the electrons in the orbitals of the atom pair up themselves, and the net momentum produced, the magnetic momentum produced, is zero, because the electrons in the orbitals pair up themselves and they are always present in pairs, thereby cancelling each other. This can be very well explained with the help of a diagrammatic representation. In this schematic diagram, you can see that the different orbitals of the nucleus contains electrons which are all paired up. They are paired in such a way that the net magnetic moment becomes zero. Here also in this diagram, you can see that in the absence of a magnetic field, that is when H is equal to 0, there is no magnetization that is visible in the atoms. But as soon as the external magnetic field H is applied, as seen here, the electrons, they start aligning themselves and producing a magnetic moment and magnetization which is in the direction opposite to that of the external applied magnetic field, thereby cancelling the magnetism and producing a net magnetic moment of the value 0. Sometimes it also produces a negative magnetism. Now let us come to paramagnetism. Paramagnetic materials can be magnetized positively to some extent when kept in an external magnetic field. The best examples of paramagnetic materials are the aluminium and the platinum, and the magnesium and molybdenum. As soon as the external magnetic field is removed, the magnetization of these paramagnetic materials becomes zero. You can see the atomic structure of the paramagnetic materials, where you can see single unpaired electrons as well, which are responsible for producing a little amount of magnetism as soon as the external magnetic field is applied. There are certain paired electrons as well, and there are certain single electrons which are unpaired electrons. So this is the atomic structure which explains that why certain materials produce magnetization to some extent. As shown in the diagram here, in the absence of any external magnetic field, that is when H is equal to 0, the net magnetic moments is also 0. The magnetic moments, they align themselves in such a way that the net result, that the net magnetization produced is 0. So in the absence of any external magnetic field, a paramagnetic material also behaves like a diamagnetic material and doesn't produce any magnetization. But as soon as the external magnetic field H is applied, the magnetic poles, the magnetic moment, they align themselves in the direction of the external magnetic field H, thereby producing some magnetization. Therefore we say that in the presence of the external magnetic field, a little bit of magnetization is observed in paramagnetic materials. But as soon as the external magnetic field is removed, it loses its magnetization. But how is magnetization produced in an atom? It is because of the electrons. There are two types of the spins. One is the spin of the electrons around its own axis, that is the rotational spin, and another is due to the revolution or the movement of the electrons in the orbitals of the atom. So the magnetic moment is produced due to the spin of the electrons around its own axis and also because of the movement of the electrons in the orbitals of the atoms. Now we are going to discuss about ferromagnetism. Just now we have discussed about the diamagnetism and the paramagnetism, which tend to lose their magnetic properties as soon as the magnetic field, the external magnetic field is removed. But in case of ferromagnetism, the ferromagnetic materials do not lose their properties of magnetization. They tend to remain magnetized even when the external magnetic field is removed. So this phenomena is called ferromagnetism. Now the best examples of ferromagnetic materials are iron, nickel and cobalt. This phenomena of not losing its magnetic properties even when the external magnetic field is removed is called hysteresis. But if it is heated at a very high temperature, then at a particular temperature these ferromagnetic materials also tend to lose their magnetic properties. The temperature at which they tend to lose their magnetic properties is known as the Curie point or the Curie temperature. Now we can see the phenomenon of ferromagnetism in the coming diagram here. Domains of magnetized atoms in the ferromagnetic materials remain aligned even in the absence of the magnetic field, but they are aligned randomly. This is called the random alignment of the different domains of the ferromagnetic materials. Whereas in the second picture, you can see when the external magnetic field is applied, the domains align themselves with the external field, in the direction of the external field. Though the fact is that even in the absence of magnetic field, they don't tend to lose their magnetic properties, and still they have certain domains which are aligned, in which the electrons are aligned in a particular direction. Therefore, in the absence of magnetic fields as well, they remain magnetized, although the different domains of the magnetic materials have different directions of the magnetization. You can also see in this picture that even in the absence of the external magnetic field, the domains of the ferromagnetic materials, the atoms in the domains of the ferromagnetic materials tend to be magnetized in a particular direction. But as soon as the magnetic field H is applied, the external magnetic field H is applied, they align themselves in the direction of the external magnetic field. The magnetic field or the magnetic momentum of the atoms, they tend to line in a particular direction of the external magnetic field. Now, to sum up, the difference between diamagnetic, paramagnetic and ferromagnetic materials is that diamagnetic materials are not attracted to an external magnetic field, and paramagnetic materials are attracted to an external magnetic field, whereas ferromagnetic materials are very strongly attracted to the external magnetic field. Just like ferrimagnetism is also one of the permanent magnetisms. And the best example of a ferrimagnetic material is that of the magnetite, that is Fe3O4. In ferrimagnets, the moments are not in the same direction. In fact, they are in the anti-parallel directions. Even though they are in the anti-parallel directions, the magnitude is not the same. They have a different magnitude in the upward direction and the totally different magnitude in the lower direction, that is a downward direction, because of which they do not completely cancel out each other and therefore give out a net magnetic moment, thereby producing the net amount of positive magnetism. The magnetism is retained even if there is no external magnetic field applied on the ferrimagnetic material. Now, magnets are broadly divided into two types, the permanent and the temporary magnets. Materials that generate a magnetic field within their own internal structure are called the permanent magnets, because these magnets do not rely upon the use of external electrical field or external magnetic field to retain their magnetism. Even when there is no external help, these magnetic materials, they retain their magnetic properties. Such are called the permanent magnets. Now let us come to the temporary magnets. Temporary magnets do not retain their magnetic properties when some external source of magnetic field or some external source of electrical current is removed. So they tend to lose their magnetic properties. Such magnets are called the temporary magnets. So many materials have the ability to inherit magnetic properties temporarily when they are close to some other external permanent magnetic materials, but their magnetic properties fade away as soon as that external source is removed. Magnets used on the refrigerators and the fridges, in the speakers, in the door locks are some of the examples of the permanent magnets. Now let us come to the temporary magnets. Now, what are temporary magnets? Temporary magnets are made up of soft metals and only retain their magnetism while near a permanent magnet or electronic current. So the best examples of the temporary magnets are that of nails and the paper clips, which retain and which gain some magnetism as soon as a strong magnet is kept near them. It gets attracted towards the magnet and become magnetized itself. Another one of the best examples of temporary magnet is that of an electromagnet, which only retains magnetism till the time the electric current is supplied. As soon as the electric current is stopped, the electromagnet loses its magnetic properties. The standard international unit of magnetic field intensity is Tesla. Our Earth, we all know, behaves like a big magnet, and the Earth's magnetic field magnitude ranges from 25 to 65 micro Tesla. How is this magnetic field produced? It is because on the outer core of the Earth's surface there is a lot of turbulent molten matter which produces convection currents. This molten matter is in a state of constant turbulence and is made up of molten iron and nickel, which are magnetic materials. And because of their kinetic properties and the continuous motion, they create electric currents, which in turn produces magnetic fields. So the magnetic field of the Earth is 25 to 65 micro Tesla. This is all for now. We will discuss about the next topic in the next part of Introduction to Physics.